Hello and welcome to yet another video of Cornerstones of Math. Today we are going to find a generalized expression for some integral, but before we get to that, let me explain some context. Today's video is inspired by this video which I uploaded a couple of days ago, which became very popular and some viewers suggested that the result from that video can be beautifully generalized. In that video we had graphs of x to the power of 1/2 plus y to the power of 1/2 equals 1, x to the power of 1/3 plus y to the power of 1/3 equals 1, and x to the power of 1/4 plus y to the power of 1/4 equals 1. And we wanted to calculate the areas of the regions between the graphs and x-axis for x from 0 to 1. I have already solved the problem in my past video, so in here I will just briefly summarize and move on. The area A can be calculated by integral of y dx, where x is from 0 to 1, and for all of these graphs, we can easily express y in terms of x, which give these integrals. All of these expressions we can easily expand, and since these are all simple algebraic functions, we can easily integrate them using the power rule of integrals and obtain these values for areas. So in my previous video, I have obtained these three areas. But we can actually keep going on and calculate more areas considering the generalized version of the problem. The general equation of the graph is x to the power of 1 over n plus y to the power of 1 over n equals 1. Then the area A of the shaded region is expressed as integral of 1 minus x to the power of 1 over n to the power of n dx from 0 to 1, which in theory you can always expand and integrate, although the expression will get quite lengthy for larger values of n. So I will just show you the results, which are these values. Now at this point, perhaps the most natural questions that come to mind are these. First, can we obtain the general formula for the area? And second, notice that in our obtained values of areas, the numerators are always 1. So it is natural to ask, is the numerator always 1? Well, to address this second question first, no, the numerator is not always 1 if we consider the most general case. For example, consider the graph of x to the power of 2/3 plus y to the power of 2/3 equals 1, which corresponds to the case where n equals 3 over 2. Then the area, which is the value of this integral, is 3 pi over 32, so the numerator is definitely not 1. And if you understand the general formula, which I will explain soon, then perhaps you will be able to find this value, or at least understand why there is pi. So the numerator is generally not 1, but as we saw, if n is a natural number, then the area is always obtained in 1 over natural number form, hence the numerator is always 1. So now I am about to explain the general formula, which is the value of this integral, but that includes some advanced mathematical concepts that are beyond the usual scope of my channel, which usually stays in high school level or at least not deviate too far from high school level. But for this video, you will have much quicker understanding if you have some previous knowledge on some special functions called beta function and gamma function, multivariable calculus, especially multiple integral, and partial derivatives and the concept of Jacobian, which is used for change of variables in multiple integral. And to be fair, many of you have already seen the general formula from the thumbnail, so I will just straight up present the result. The general formula for the area, which is this definite integral, is equal to gamma function gamma n plus 1 squared divided by gamma of 2n plus 1. Here, this gamma function, which is the extension of a factorial to complex numbers, is defined as gamma z equals the improper integral from 0 to infinity t to the power of z minus 1 times e to the power of minus t dt. We are dealing with positive numbers n, where this gamma function is well defined. So using the values of the gamma function, we can calculate the area for the general case. But let's take a look at some special case of interest, where n is a natural number. I've said that the gamma function is sort of generalized factorial function. So when n is a natural number, the gamma function simply gives factorials. More precisely, gamma of n equals n minus 1 factorial. Therefore, if n is a natural number, then the formula reduces to n factorial squared divided by 2n factorial, which is equal to the reciprocal of the binomial coefficient 2n choose n. So we can see that the numerator becomes 1 if n is a natural number. So now that I've introduced the general formula, I will show you how this formula is derived. So first, we obviously have this integral, but this x to the power of 1 over n can be quite the hassle, so let's use substitution to change that. We let x to the power of 1 over n as t. Then x equals t to the power of n, and dx equals n times t to the power of n minus 1 dt. And the interval of integral does not change, so we have integral 1 minus t to the power of n times t to the power of n minus 1 dt. Let's take out n to the front and write it as integral of t to the power of n minus 1 times 1 minus t to the power of n. The reason why I am doing this is because this particular form of function also has a special name, the beta function. It is a two-variable, single-valued function defined as beta of z1, z2 equals integral of t to the power of z1 minus 1 times 1 minus t to the power of z2 minus 1 dt, t from 0 to 1, which is a different interval compared to gamma function. So by observing this, you can easily notice that our area can be expressed as n times beta of n, n plus 1. So we have the area expressed by beta function. And the reason why I bother to express the integral in terms of beta function is because then we can use one very special property of the beta function, which relates the beta function to the gamma function that I have previously mentioned. And that will be the lemma that allows us to express the area in terms of gamma functions. Two functions are related as follows. Beta of z1, z2 is equal to gamma z1, gamma z2 divided by gamma z1 plus z2. So now let us prove this lemma. I will start from gamma z1, gamma z2 and show that it is equal to beta z1, z2 times gamma of z1 plus z2. So we have the product of two gamma functions, so let us express them using variables u and v for integrals. The first gamma function containing z1 is expressed as the integral with respect to u, and the second gamma function containing z2 is expressed as the integral with respect to v. And now let's do something that might be quite familiar to you if you have learned the multivariable integration. From the perspective of this integral for v, u can be considered constant, and from the perspective of this integral for u, v can be considered constant. Therefore, we can write this as an iterated integral where every function is crammed in the middle. Here, let us combine this e to the power of minus u and e to the power of minus v to write it as e to the power of minus u plus v. So we have this. And some of you might know that you can express this as a double integral, where our domain of integral x is the region that u is from 0 to infinity and v is from 0 to infinity. So basically, this entire quadrant. But here's the thing. We want to prove that this integral is equal to the product of some beta function and some gamma function. But if we take a look at the interval of each function, the gamma function has an interval from 0 to infinity, so it won't be a problem, but the beta function has an interval from 0 to 1. However, in our obtained integral, both u and v have values from 0 to infinity. Therefore, we need change of variables. That is, we have to change the variables of integration u and v into new sets of variables s and t, so that in our new domain y, s still changes from 0 to infinity, but now t changes only from 0 to 1. But how can we achieve that? Well, let's think about our end goal here again. We want this integral to be expressed as a product of beta function and gamma function. And notice that the gamma function has e to the minus t here. Therefore, we should change this u plus v into a single variable, say s. And now the second variable t, which should only have values from 0 to 1. And we can achieve that by defining t as a ratio. More specifically, let t as u over u plus v. Then you can notice that when u and v can have positive real values, the value of t is confined from 0 to 1. So we have s and t, but in order to use the change of variables, we actually have to express u and v in terms of s and t, and you can easily find that u equals st and v equals s times 1 minus t. Or you can say that u, v is given as a multivariable function phi depending on s and t, which is defined as the vector-valued function st, s times 1 minus t. In this setting, the change of variables works like this. du dv equals ds dt multiplied by the absolute value of the determinant of this 2x2 matrix, which consists of partial derivatives of u and v with respect to either s or t, where this determinant is called the Jacobian determinant. So by taking partial derivatives, we obtain this matrix, and you can easily find that this simplifies to just s. So we have du dv equals s ds dt. Therefore, the integral is now expressed like this. We have new domain y, and u is changed to st, and v is changed to s1 minus t, and we have ds dt multiplied by s, which comes from Jacobian. And from here, it is essentially the reverse process of what we have done. First, we can write it into iterated integral form, now with s from 0 to infinity and t from 0 to 1. And if we rearrange the integrand function a little bit, we have e to the power of minus s times s to the power of z1 plus z2 minus 1 times t to the power of z1 minus 1 times 1 minus t to the power of z2 minus 1. And then we can split this into the product of two integrals. And by comparing with definitions of beta function and gamma function, we can notice that it is beta of z1, z2 times gamma of z1 plus z2. So there we have proved the lemma. So now with the lemma proved, let's move back to here, where the area A is expressed in terms of beta function. By applying the lemma, we obtain n times gamma n plus 1 divided by gamma 2n plus 1. And the gamma function have this property, gamma n plus 1 equals n times gamma n, which follows from simple integration by parts. And we can use this property to change this n times gamma n into gamma n plus 1. That gives gamma n plus 1 squared divided by gamma 2n plus 1, which completes the derivation. So to summarize, the area of the shaded region, which is this integral, can be expressed in terms of either beta function or gamma function, or in this way if n is a natural number. And that's all for today's video. Thank you for watching, and please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.